All right, so today I'm going to focus on big picture things related to structures. And starting here with just how structures come about, right? Well, first of all, society determines a function, and that function is based on some kind of need, right? Then the architect is brought on board to determine a configuration, right? A layout, shape, size, things like that, that will serve that function. And then once that initial configuration is established, then the engineer is brought on board to make sure that it obeys the laws of physics and things like that, right? Determine the details of the structure, size things, design connections, all of that. Now, I don't think this was included in the slides that I published to D2L for you, but I did throw this into the syllabus because I think it's just the perfect script for his class. So if you can't read it, it's Calvin asked his dad how they determine the load on bridges, and his dad says they drive bigger and bigger trucks over the bridge till it breaks, and then they weigh the last truck and rebuild the bridge. And then his wife gets mad at him because that's nonsense. So yeah, it is nonsense. That is not how we, design things or determine the loads on things, of course. However, there is a grain of truth in that when things fail, we learn from those failures, right? And sometimes things fail because a load comes along that was not expected, or something happens that there's a phenomenon that wasn't fully understood at the time of the design. So we learn from those failures. And this is important because, right, as civil engineers, and this isn't just true for structures, but all civil engineers, right? Whether you're designing a wastewater treatment plant or a water distribution system or a road or transportation system, we do not have the luxury of developing full-scale prototypes and then subjecting those prototypes to hundreds or thousands of tests before we release our design to the public and then mass produce it, right? So we don't have that luxury. So we have to rely on our analytical models and collective years of experience in the industry, right? As well as our knowledge and understanding of the fundamentals, mechanics, dynamics, statics, things like that. So I think that's important, right? An important distinction there. So here are several of the main responsibilities of the engineer, right? The ones in purple box are the ones that we're going to focus on in this class. These are listed roughly in the order in which they would actually take place in the real world, right? So first up, develop a preliminary design. That's something that's truly the role of the architect, right? That's in the architect's responsibility. But a lot of times the engineer, maybe not a lot of times, but sometimes the engineer is brought on board at that early stage, which is really nice because then you can work together with the architect to figure out the most economical solution that meets the needs of the client, right? And then, again, now we're getting into what we're going to focus on in this class, right? Specification of loads and their placement. Up until this point, right, in statics and mechanics, you have been given loads and asked to determine the response of the structure. You're still going to be doing that in this class, but in this class you're also going to learn how to determine what those loads are in the first place. So that's a cool part of the class. And then preliminary estimation of member sizes, right? So that's approximate analysis. Now that's something that we're not going to talk about until later on in the class, but in the real world that's something that you would do early on in a project. Modeling the structure is referring to a refined analysis, right? This is your in-depth calculations, determining stresses and strains and things like that. In this class, we're not going to be dealing with stresses and strains much. We're going to be relying more so on statics and dealing with internal forces and reactions. But don't worry, stresses and strains aren't done with you yet. If you were concerned about that, you'll get more of that in structures too. And then we analyze the response of that structure using mechanics, so that ties into what I was just talking about. All right, so, and then after we've analyzed the response of the structure, then we size members and connections, evaluate serviceability, safety, and durability, and assess any special requirements during construction. So these two bullet items are directly tied to designing the members, and that's what Structures 2 is going to be focused on, right? So Structures 1 is more focused on the analysis, Structures 2 is focused on design of specifically steel and reinforced concrete. So once we get into design, we have to be material specific, because as you remember from mechanics of materials, right, Young's modulus, shear modulus, those are all directly tied to material properties, and then that's how you determine stresses and strains, and then that's what drives the design. All right, so you've already taken statics and mechanics. Again, structures focuses on analysis, structures 2 on design, and then if you're still interested in structures after structures 2, you have the option of taking some advanced courses. Those are usually material design courses like reinforced masonry, wood design, steel, things like that. Or at the 500 level, right, there are some graduate level courses like dynamics of structures, which is completely different from eGen 202, completely different. I will even say, all right, there is one prerequisite for structural dynamics. One prerequisite. What do you think it is? You're close. Huh?
Dynamics.
You would think it was dynamics, but it's not. It's structures 1, it's this class. Yeah, but yeah, you would think that, sure, logically, eGen 202 would be a prerequisite for structural dynamics, but no, it's not, right? So structural dynamics, it's completely different. It's its own thing. You don't need eGen 202 for it. So maybe a sigh of relief for some of you, maybe not, I don't know. But it was one of my favorite classes that I took in graduate school. All right, so now we'll go through a few definitions of these terms. First up, structural system. This is an assembly of members that are interconnected by joints. The main function of this system is to provide a load path that will carry loads from the point of application, wherever that may be, right, the roof, the sidewalls, inside the structure, whatever it is, from those points of application all the way to the foundation while maintaining the integrity of the structure. Oh, and by the way, these slides are posted and published on D2L for your reference. It's not super essential to have them in class for note-taking, but some of you may want to have them. All right, now structural behavior is the response of the structure to applied loads, right? And that includes environmental loads. The structural response could be internal forces, deflections, whatever it is that you're looking at. Now in this case, we see diagonal cracking in the masonry or the brick facade. So that diagonal cracking is a sign of lateral loads. That was probably caused by an earthquake. That brick wall that you see is not part of the structure, right? I should say it's not part of the structural system. It's a facade, right? It's architectural. Behind that brick wall, there's probably a shear wall, maybe made of concrete, most likely could be masonry, or maybe it's a steel braced frame or a moment frame. All right, we're going to talk about all of those next week. But my point is that behind that brick facade is the real structure that's responsible for transferring those forces safely to the foundation. So the cracking that you see in the brick is not necessarily a sign that the structure is going to fall down and crumble, right? But it is a significant red flag, so this would need to be inspected thoroughly before it was flagged as safe for reentry. All right, now structural analysis refers to the determination of the structure's reactions, member forces, and deflections. You all already know how to do these things from your previous classes. So again, in this class, we're going to build on that. You're going to learn some new analysis techniques to get there, and we'll attack some more complicated problems as well. Analytical models are what we use to predict the behavior of the structure. All right, now there are many software programs that we use in the real world. And for a given project, you might have 20 or more different models of the same building using different software or maybe different models within the same software to handle different load cases or load analyses. Depends on the project. But in all cases, it's so important that you always use engineering judgment, right? You probably heard the expression garbage in, garbage out, yes? Well, that couldn't be more true in this case, right? The program will do exactly what you tell it to do. So it's important that you understand what it is you're telling it to do, right? So you need to know the specifics, the quirks of that particular program, right? What are the default settings? What are the assumptions that that program makes? And how does that program actually come to its results, right? And that's what we're going to expose you to in this class, is how those programs generate those results. So, all right, so yeah, so it's always important to use engineering judgment. Now, these are the primary considerations when we design structures, right? So this is just an overall general, again, big picture view. First up, stability. This means that the structure has to maintain its shape, right? So after loads are applied, the structure should return to its original position. It doesn't mean that the structure shouldn't move at all, right? We know that the structure will deform or deflect when loads are applied. That's mechanics, right? But once those loads are removed, it should maintain its shape. And then we've got strength and stiffness, right? These two things are not the same. Strength refers to the ability of the structure to safely carry the loads from the point of application to the foundation. Stiffness refers to the ability of the structure to not deflect too much, right? So stiffness is tied to deflections, while strength is tied to safety, etc. All right. All right. At some point, I had something else that I meant to mention, but I forgot. All right, I'll come back to it. Now, last but not least is economy. All right, so this is tied to constructability and life cycle costs. And this is, there's multiple balancing acts that are tied to this within structural engineering, right? So one of the obvious factors that goes into economy is the material economy, right? So how much do the materials cost? But if you design a structure to be 100% optimized for material, it's going to be really difficult to build, right? So you're going to really skyrocket those labor costs. So there's a balancing act there, right? And essentially, the more materially efficient the design is, the more difficult it will be to build. I remember what I was going to point out here. All right, so this is back to the stability thing. Right, when I said that the structure needs to be able to return to its original position after loads are applied. And you all know this already, so who remembers what that is tied to from mechanics of materials, or what that's called?
The proportional limit?
You're absolutely on the right track there.
Strength?
Yep, so the stress strain curve, right, and what does that proportional limit distinguish between?
Like before it returns to its original state, or to where it gets to the point where it's not going to be able to?
Right, once you get beyond that, what happens? Yeah, it'll have permanent deflections, right? Yeah, it's elastic versus plastic behavior. Is that what you were going to say? Yeah, excellent. Yeah, so elastic behavior. And elastic behavior is what we typically assume for our analyses in this class. In advanced topics or advanced structural analysis, you'll have to consider plastic behavior. This is really relevant for seismic analysis. But to start off, we're gonna stick to elastic analyses. So, all right. So moving on to limit states. I'm gonna check the time here. Okay. So there are 3 different limit states that we design to in structural engineering. Right. The first and most important one, of course, is strength, because this is tied to safety. And the criteria for designing to strength are outlined by the building codes. And these codes are the law of the land, right? So the codes are informed by industry standards, which are developed by experts in the field. And then when those codes are adopted by a jurisdiction, right, governing jurisdiction such as a state, then it becomes a law. So different states have their own different codes, but most of them refer to the same document. And then we have serviceability, right? So this is tied to the function of the structure. And some of the serviceability criteria are in fact outlined by code, but most of them are determined through recommendations or industry standards. So an example of serviceability, right? Again, it's tied to the ability of the structure to maintain its function, right? How many of you have been in a building where the floor shakes just because somebody walked by? Yeah, I think a lot of us have experienced that, right? So that might be perfectly acceptable in a residential building or an office building, for example, but in a hospital, that would not be okay because hospitals have very sensitive equipment that cannot be subjected to those types of floor vibrations. So the criteria that you design that sort of thing to is tied to the function of the structure. Another example would be with high-rise buildings, right? So tall buildings will sway in the wind, and that's okay. We know they're gonna move in the wind like that, and we want them to. But we don't want them to move so much that the elevators can't function, right? And then lastly, we have habitability, which is tied to human comfort. The criteria here are outlined by recommendations or owner request. And this is tied to lateral accelerations that are experienced in, again, typically in tall buildings under wind excitations. So you don't want people to be getting seasick in their penthouse condo up at the top of some fancy high rise. It happens. All right. So, a little bit more on strength. This is the Tacoma Narrows Bridge. I selected this because I emphasize that this means the structure must be able to resist expected demands. And if you're familiar with this failure, right, the Tacoma Narrows Bridge was, a very famous historic failure. Fortunately, no person died. I think a dog did perish in this. But this bridge failed due to a phenomenon called flutter. This is a dynamic phenomena that engineers were not aware of at the time that this bridge was designed and built. So this is another example of, right, going back to that Calvin and Hobbes comic strip. Well, at the time, they didn't know about this. It failed. Now we know about that phenomena. So now our bridges are built with that in mind, right? So we think about that. Yeah, back to that. All right, here's another example. This was a historic bridge in North Dakota, a 56-foot long bridge, I believe. It collapsed in 2019. The posted limit was 14 tons, and the driver either didn't see that, giving him the benefit of the doubt here, or decided to shrug it off and drove over that bridge with a load of 42 tons. So surprise, it collapsed. Fortunately, nobody died, but it is a significant loss of a historic structure, right? So I'm sure it was replaced by something more modern, but is anyone here for this? A few of you were here for this? Okay. So what was this, 2019, I think? The South Gym roof collapsed on MSU. We'll talk about this more when we get to snow loads, but this was essentially following a series of unfortunate events. And I don't believe that this was due to any expected load scenarios. So I think it was overloaded beyond what it was designed to support, and then that's what led to the failure. All right, so now a little bit on serviceability. All right, so this is a structure, another historic structure in Napa, California. In 2014, a magnitude 6 earthquake damaged this building. It was eventually renovated and reopened, but, right, so it didn't fall down, but what's off with this?
It's like it's shifted to the right.
Yeah, it's leaning significantly, yeah?
Mm-hmm.
So So yeah, the maximum lean on this is 4 feet, and that's at the top. Sorry, my screen's showing something different here. All right, so this is at the top, right? The maximum lean is about 4 feet. So that's obviously not cool. They did eventually, right, rebuild this, or rebolster it, right? So they had to support it from the outside before they could get in there and fix the inside. But a lot of older structures, especially older wooden structures like that, were not designed to resist earthquakes at all. In fact, there are a lot of historic structures in Yellowstone National Park that have been renovated to resist seismic loads now. The Old Faithful Lodge is one of them, and they've been done so in a pretty thoughtful way. So, for example, you wouldn't know it looking at it, the Old Faithful Lodge, but they maintained the original mass timber columns, and they just hollowed them out and put some steel frames inside. So they've got the new structural system hiding in the old structural system, which is pretty cool. But not all buildings have been updated. It's not required unless they want to go through a significant type of renovation, and then that triggers the code requirements to upgrade it. And sometimes they choose to not go that route. All right, and then finally, lateral accelerations. Right, this image says it all. All right, so now, quick question here. Do we have a strength or serviceability issue in this image? Serviceability? Strength? Yes, both. So I would say definitely strength failures, right? So this wall, there was a wall here that has just completely fallen out of plane, so this is an earthquake. You can see this wall has completely sheared off from the connection to the roof. The floor is sagging significantly, right? So it no longer has the support along the edge. So that floor is sagging significantly. So you could argue that, the floor itself hasn't failed. It depends on what criteria maybe you're considering. Has it yielded? Maybe. If it's yielded, then it's probably failed. But you could argue that, that's still meeting its strength demands. But I wouldn't want to test it out by putting any more load on it, right? So definitely not safe. All right, so real quick here. Which of these is a simply supported beam? One on top is a simply supported beam, yes. What about this one? Is that a simply supported beam? No, it's not, because we have the overhang, right? We could call that a simple beam with an overhang. What about this one? Is that a simply supported beam? No, we call that a cantilever beam. All right, so there's only one correct answer for simply supported beam. That's a beam with a pin on one end and a roller on the other. So that's just one thing that we should make sure that we're all on the same page with. All right?
Sorry, is this parallel processing?
Not yet.
Oh, okay, sorry.
Yeah, we're just ending. We'll be out in a sec. All right, so we'll stop there today, and thank you all for your attention. Friday, we'll start lecture 2.